So in the first lab, we have three tasks to turn on the LED or to blink the LED using INO assembly and C. So first of all, we are using INO. In INO, we don't have to do much effort. Just we can go to the examples and basics. In basics, we can access the blink code. When we get this, we just have to make its hex language or hex output by upload export compiled binary. Then in Proteus we have to upload that binary. I have already saved it in my labs, so I just initialize it and we can see here it's blinking now. In the second task, we are using assembly language. In assembly there is a bit change in syntax. First we initialize the register in which we want to operate it. So for output we give it the maximum value 0 cross ff means 256, and then ddrb for the initializing port we are using b port. Then we use the SBA command for the port of pin number. Here we use fifth pin and then delay and then again the loop, and then we compile it. This code is already once compiled, so we have to make a new one. Now control and assembly file paste here, and then oops, we have to hit new project, not file. Wait, we are using AVR 328 Arduino Uno. Place this my main code or the code given in the user manual. So first we have to select that no, we are not using the main project, we are using simulator. Again start. Once it has done the loop, so we can get its hex file by containing path, and here we have the hex file. Just upload this hex file. So for I am pasting it here so I can easily access in Proteus. Here we can access this by quick desktop, and here we have the LCD project. So sorry, assembly, and then start. Now you see that the time lapse is short because in assembly we are using a short loop and giving it much small delay. In the third task, so here the third one, we are just we are using C language and everything is same like in the assembly. We are initializing the same port B and same it's pin 5, just making a delay bit shorter. Like now we are using 100 milliseconds, means we can just barely see the blinkage in the Proteus. So let's check. Wait, lab 1, I'll just do it. Here now in the third one, it's too much No, it's completely a 1 second. Sorry, it's my mistake. It's 1 second, not 1 millisecond. So this is our lab task one. So in the second lab we have 5 tasks. So in the first task, I don't remember correctly. So let's see what's the first task. So in the first task, what we have to do is first we have to initialize a register. So we are making it as output, so we can initialize it with the maximum value 0 cross ff. Then in the line 1, so then line 1 we are giving it to the port B and then loading the R20. So here we are giving the port B two values. First we give it the value of R16 and then we give it the value of R20. So first we are giving the maximum value 0 cross ff. In hex means it is the 256, and then we give it the 0 value. So first let's see when what's the output when we project file project assembly 328 p replaced. So first let's see input output ports, registers, CPU registers. Here we have CPU registers. So the first line, what we are doing is, as you can see, we are initializing LDI with maximum value. When we jump over here, we have the maximum value at 16 register. Then we jump again and initializing the R20 with the value of 20. Here we see that in the R20 we have 0 value. So now we have to see that where is the registers. So on the port B, as you can see, in the first we are initializing 0. Then on the port B we have the value of R16. Then again we are here, you can see that on the value you have again the 0 value. So it means our code is right and it is working now. So if you must see its procrastination, you can here see that easily on the desktop, lab 2, assembly, debug file, hex file. Here now we are not initializing any port or not giving any value to the LED or anything else, so we cannot see mainly anything new here. So its process is just a formality. Mainly we are just understanding that either we can change the values or not by using registers. So our task is complete here. Now in the next lab task, let's see. So here, now same here. Now we are assigning, first we are assigning the LDI or 16 zero value, then initializing maximum value to the register 17. Now in this we are using two ports, DDRB and DDRC, instead of one, and using a port as an input and the other and another port as an output. So we have to remember that when we are using a port as an input, we are giving the value, we are giving it as the zero value. So DDRB is using as an input, so we are giving the R16 zero value, and DDRC as an output, so we are using it, giving it maximum value of 0 cross FF. Here we can see that first we initialize R16 as a register, as an input register, so we are giving 0 value. Then R17 as an output, so we are giving the maximum value. Then initializing the ports DDRB and DDRC. Finally on our R18 we are giving the value, we are getting the value from port B R16, and then the output value on port C as R18. Like in the Arduino we have using two pins, like I have to select a port for a button. From button I can give it the input, like when I want to turn on the light or I want to turn off the light. So here suppose this, the port C DDRB is an input, we are initializing the button on the input, and then we are uh, uh, then we are using port C as an output, like when I push the button, so it gives the value to the DDRB, and then the command executes on the port C. So I have to use the port C pins as an output. Like we have 5 pins. In any pin, when we put the LED button, LED light. So when I push the button, all the ports have the value of maximum value. So for proof check, I just put the code here and let's execute it. So you can see that the code is working 100%. Here we use the R16 as an input, we're giving it the 0 value, then R17 the output, then DDRC and DDRB as a ports input and output ports. Here R18 we are taking the value from pin B, and then we're giving it the output to the R18 on the port C. Doesn't matter we load a register how many times, because LDI is just a temporary command. We can use it many times, and we can use a same register with many values. So we have the task 2. Now I don't think so here in this task we have any confusions. Let's see what we have to do in the task 3. In the task 3 we have 3 LEDs, we can use 3 to 4 LEDs, and we have to blink each LED one by one. So basically here we can use the same command with delays. Like when I want to skip the command, we can use a delay, like a time in which a command execute in, like in 1 second. We can step over to the next command. In that 1 second the LED will be shut off. So we are using R19. So here we don't use any inputs, so just we are initializing only one register with the maximum value R19. And DDRB means we are using the port B. It means we are using all the pins of port B. Here we are using the SPI command. Port B0 we are initializing the zero port 0 b 0 pin of port B. It means on the 0 pin the LED will the LED on the pin 0 will blink now. Then after a delay the LED of pin port B pin 1 will blink. Then after a delay, here we are using the CBI and SPI commands. SPI means we are initializing the ports, and CBI means now we are clearing it. Once, because if you don't clear this, then when the second LED will blink, the first also on is on the on mode. So if we don't use that command, at the last night all are on. So we are using, because our task is to blink only one LED at a time. That's why we are clearing after each LED will blink. So here we are using, and now we are using the decrement command. Means we are just blinking it like for some time. Here we are using the 69. It means we are blinking at 69. After that time, or at that period, there will be no LED that is blinking. So as we can see in the lab, first we proof check that code, that is it working or not. I don't think so that it is not working. Let's see. Control V, debug the file. So now we see that R19 we have already done it. Now that is just delays. We can't understand it here, so we are using the Proteus for that. Task 3. So in the task 3, lab 2 dot hex. Okay. Oh, I'm sorry, we're just using lab task 2, so I don't think it will work. No, we we have to open the task. Oops. Wait. Task 3. I have to open the task 3. Here we have the lab task 3. So let's see that is it working or not. First I have to get my file. Containing path. Here is our file, the hex file. Copy, paste it here. Now from the Proteus Laplace 3, Laplace 3 desktop. Now you can see that they are blinking now. That this is the task we have to do in the this is in the task 3. Now we have the task 4. I really seriously I don't remember what's the task 2 we have done in the lab. So let's see it together. From the code we have to understand. So here we are using two registers. Both are our input registers, so we are giving the 0 values. So and in the third we don't have to do much effort. Just you see, when you are giving the 0 value, it means you are initializing it as an input, and as you can see, these two are input registers. It means when we are using R20 and R21, we are using it as the input. So in this we have two inputs, and which two ports are we using is port C and port B. And then on the port D, we are making it the output port. Let's see what we are doing here. So here we give the R22 a binary value. It's up to you that whether you want zero, whether you use a command of 0B11, or you can use it like 0 cross 22. Both have the same output. So here we can see that first we can take the values from the we can take the values from the R17 from on pin C and take the value of R18 from pin B. Then we can subtract both of them and make the output on the R17. Like here we are using 22 and the other is 44, I think. And after the subtraction we have the output on the port D, and then to the again. So basically in that code we are initializing two registers R20 and R21 as an input registers. Here we are giving them the 00 values, and on the output we are using the port D as a register to R25 and giving it the maximum value. When we can add the both registers, we just have to subtract them and show the value on the and show the output on the port D. Let's see that is that code is working or not. Control C. So here we have a great first make it clear. Control V. So as you can see we have the values 00 values, and now on R25 we have the value of 0 cross FF. Before we have the 0 value, so we don't see that there. And you can see on the R20 we have the value of CC because you are initializing that. No, when we subtract them, we have the value of other R17. So here we just understand the commands of negative and positive. But mainly what are you doing is you can get it from the code. So go to the main assembly, copy that, put it on the desktop and paste it here. Replace that file, go to the Proteus, open the task 4, turn on the, here we have that assembly. So here we have the output. As you can see that we are we're just blinking all the LEDs, and I don't think so that we have that this Proteus has any logic with it. But that was too old, so I don't remember what was the real instruction for that lab. So basically just we have to understand that we are using two initializing pins. Like I am using pin B and pin C. I have two buttons. Like when I put the both of them, when I push the both together at same time, then we can see the output on the LED from port D. But after the first time the value will be decreased to the first one. So on the second time when we push it, there will be no any there will be no any there will be no change on that time. So that was the task of lab 4. So let's go to the final task of the lab, the task 5. Let's see what we have to do is first we are initializing the R16, then we are giving the com command, then increase the 16 value, then initializing the R17 with the value of 30, decrease it, then add both of them, move R16 and 17, store the value to the address of 16, subtract it, and jump it again. So here we are not making too much circuits and any other thing, just we are using some commands like the com command and the decrement command, the add command, the command of movement, and the command of storage, like how we can give an address to some value, or like this we have, like in the Arduino we have too much addresses, all are on the general at the null storage, so we can assign values to that addresses. We are just assigning the addresses with some values using the registers, not much things. Like here first we initialize this, then this, then this, and this. So I don't think so that there we have too much fuss. So that's the lab 2. That's it. So here in the lab task 3 we have two tasks. Let's see, it also have, so the first task is the 7 segment counter and the second is the hex keypad. As we already know that what the 7 segment counter is. The 7 segment LCD display, in this display we have 7 LEDs. I don't remember that one was working, but the code was accurately right. So let's check the codes. So first of all, we are giving the delay, adding libraries, initializing the port DDRB and DDRC as the LEDs to show the values of LEDs. So we don't use any hex keypad or push button. So we just giving the output commands and initializing with them with the maximum values. Here we are giving the value 0 cross 3F for the first LED, the second LED, the third LED, the fourth LED, the fifth LED, the sixth and the seventh. These values are for the value of when we want to play the 1, we use that command. When we want to play the 2, we use that command. For 3, for 4, for 5, for 6, for 7, for 8, for 9, and then the 0. These are the hex values that are using on for the counter. We don't understand what you don't understand what I'm saying until unless I execute it on the Proteus. So make a new project. Here nodes GC executable library 328p, and here we have the control V, and now let's see. It means our code is working. Okay, do impossible, possible, possible. So as you see that we are using the two registers R16, and then so what we are doing here is don't understand until I copy the path from Control C on the desktop, Control V, copy paste here, open the Proteus and execute the file here. Let's see how the counter works. We are not doing just too much effort here, because in the C everything is so simple. We just really have to initialize the two LEDs on the ports. We can check the ports by their datasheet on the Google, as I already do with that thing. Now just open and start the counters. So as I already told you that the pins may have fault, but in the class it was working much good. So wait, I think I have already do it. Maybe that, no, this was still working. Let's see. No, not even that one. So as I already told you, that was too old. So maybe I am not opening the same files, or I'm not getting it. Maybe that one was working. No, that one was so not working. The final option was the code that I uploaded here. That one. As you can see that we are already initializing the maximum values. It means other values are not showing here. It means our code, that the code I use here was a bit faulty. But now this is now you see that the delay was too much long. So it's working, but it is working too much slowly. And I don't have too much time that or to play it or pause forward. So as you see, that hex is still working now. Even my current hex file is not working, but that one is also working. So that was the task one. Now go to the task two. What was our second task is to initialize the hex keypad. First open the hex file, and second open its assembly. In the hex keypad we mainly use column or row numbers. So in the hex files, so in the second lab task we are initializing the hex keypad. As you see in the first task, how to use 7 segment display. then we are using hmm? then we are using the hex keypad with 7 segment display. So in 7 segment display we have 4 columns and 4 rows. So it's up to us that whether we are initializing the keypad using columns or using rows. In my in my task, I think I use the columns, like 4 columns, and with the and with the respect of each column, and with respect of each column I initialize the 7 segment LEDs. So first of all, let's see the code. Here we have the code. So like we have 4 columns, then we are using 8 ports. So in column 1 we are using on port D. For the one value we are giving it the value of 1. So this code is for the 7 segment display, because that value is for the value of 1 on the 7 segment display, like only the one LED blinks in that display. For the second value we are using this, and after each value we are clearing that. So no shuffle, and so to prevent the shuffling, in the column 2, in the first column we have three values like 1, 2 and 3, and in the no, sorry, in the first column we have three values, 1 4 7. In the third column we have values 3 6 9, but in the second column we have four values, 2 5 8 and 0. So in only the second column we have four values, you can see that. So as you can see that this is the main code. We have the main code. Now for the proper working, here we are not using the we are not using the 7. So as I already told you that we are not using the 7 segment display, we are just using it, just checking it. So let's see, like in the third we are using third column, then it means we are initializing the third value. And I also remember that here we can see that we are not clearing the value. It means once I put the I put any button, the command execute, but the second time nothing will be work. So it's the main code, so I'm not changing it now, because that was working on the that was working exactly in the labs. So I'm just showing you that the code was correct, like here. Or again then we are using that, like here, because that is these are just some 4 LEDs and the code I am using is the 7 segment display. So we're for that we're using minimum 7 LEDs, but not here, we're not using it here. So our task is just done here now. You don't have to do much effort for that, because it's just done. So as I already told you that we're not using the 7 segment display, we are just using it, just checking it. So let's see, like in the third we are using third column, then it means we are initializing the third value. And I also remember that here we can see that we are not clearing the value. It means once I put the I put any button, the command execute, but the second time nothing will be work. So it's the main code, so I'm not changing it now, because that was working on the that was working exactly in the labs. So I'm just showing you that the code was correct, like here. Or again then we are using that, like here, because that is these are just some 4 LEDs and the code I am using is the 7 segment display. So we're for that we're using minimum 7 LEDs, but not here, we're not using it here. So our task is just done here now. You don't have to do much effort for that, because it's just done. So in the lab, for first sir told us to just the interface the LCD 16 by 2 LCD to the Arduino. Then on the campus sir just change it, the task that we are not using, not just using the LCD, we also have to initialize the hex keypad and then use it again. And then we have to show the output, we have to get the input from the hex keypad and show it on the 16 by 2 LCD. So in the first, so and for that sir also gave us the header file. I think I have that one. Yeah, that's it. So as you can see here, we have the header file. We are also adding in it, we have the main code. Like what we have to do is we have just initializing the rows and the columns. We have to using the CMD commands. The code we don't do too much things, we just have to display that by initializing its bits and cursor. Like we are using why we are using the cursor, like to you shift the ports. We have 16 by 2, it means we have 8 bits on the first column and first row and the 8 bits on the second. By using cursor we can shift the bit from 0 to 7 in any of them blocks. So for that, sir give us that header file. Here we have the header file. The main code we are just initializing the ports and using that header file that was also uploaded on the GCR. We just have to change some things. That code was used just for the online labs, but when we are on the campus, sir told us that we have to initialize the hex keypad, as you can see here. And and here we don't have to do too much trouble, just use that same code that we use in the lab, in the second task of the third lab, for the hex keypad, and initialize it according with the 16 by to the LCD. Here we can see that first hex to LCD, like I put 7, I put 8, I put 9, I put 7, I put 0. As you can see that, just that that's it. We don't have to do too much trouble here. And I don't think so that in this lab we are doing much effort, because we are just combining two things. Like, we already know how to use the LCD, we have the header file, we just initializing the ports from D0 to D7 to make the for the 7 bits, and the enables for the control of LCD, and the VCC for the power of the LCD. In the physical LCD, we have too much ports for the A and K for anode and cathode for the backlight of the LCD. But here we don't have those ports because we don't need any backlight on the protest simulation. So here we are done with the first 4 labs now. So in the fifth lab we just have 2 tasks. In the first task, we have to just show the this just to display counter clock on the 16 by 2 LCD. I don't get it because no, yes. Because in the lab 4 we just initialize the LCD, but on campus sir change the lab task and we have to initialize the LCD with the hex keypad. But the lab 5 was same. In the task 1 we just have to show the counter, like when I play that, it will show you the overflow 0 1 2 and so on. And the hex in the file same, we use the hex keypad hex file of the hex file we use, that's uploaded on the GCR. And in that we just don't do too much effort, just initialize the values and make the time and use the timer TCNT and nothing more. So here we are done with the lab task 1 of the lab 5. Then we are going up to the second task. I don't remember what was the second task we have done in the early first half of the semester. Let's see what was the first task, and here we start the first task. And I now see that here we are using just time. We are using the clock and the same thing that we have done. So I don't think so in the lab task 5 we are using too much things or effort. We are just changing the cursor and using the first 8-bit and not using the second 8-bit. It's up to us that whether we want to use the first 8 or the second 8, but we are using just the first 8 bits here. So we are done with the lab task 5. Now let's go to the lab task 6. What was the lab task? Yes, here we have the SRI and UART, SPI and UART, serial peripheral input, and the UART was here. We are using two microcontrollers. One for the input and the other for the output. So in the second lab, as you can see, we are using two microcontrollers. For the first controller, we are giving the value to the first controller, and from UART, here you are using SP and UART because they are for the parallel connections and use for the short distance and the best data coverage, like amplitude, frequency, and like amplitude and frequency. We are for one is for the short range, another is for the long range. Same in the like in same in here. We are using the parallel connections here in as compared to the serial one, and here we are using the uh, asynchronous connections, in which we have to use the external clocks. There are three types: UART, use art, and I2C, but the laptop was just for UART and the SPI. So in the SPI, what are we using here is the SPI, as you're seeing. Here we have the code of the slave, and the other was the slave for the code of master. Nothing much effort we are here applying. So here is the UART and the SPI. Both are approximately similar, and I don't think so in the lab 6 we having so much issues and problems. Here we have the also we can run the code. As you can see here, let's enter the hex file that was generated here. The last lab 6, and here we have the UART and RX file. RxTX are just for the data transfer of the files. All we have to do is so here I think I just put the wrong files here. Let's check that again. I was using, so yes, I'm using USPI and I'm uploading the UART files. That's why it's not working here. Let's make the mistake right now, using the master one, and then the art. Where you see your, because here we have the space. So here is the slave. So now it may be fine now. Still not working. Not getting this. Let's check this by replacing their files. Still don't remember why this. Oh yes, my mistake, because I'm uploading the opposite ones. I'm uploading the master's file on the slave one and the slave file on the master's one. That's why you are. No, it's exactly right, and I don't think so that now it has some issues. Why the hell is still not working? That one is the slave and that one is the master. So I'm not really don't get it. So just let's see the code. Once if we can overthrow from the code, and then I'm not using that or seeing it again. I'm mostly done with both fun one from first 6 labs. Now I'm uploading it. So let's stop it here. So in the lab 7, we are using we are using LCD and initializing the two buttons as an input and showing the output on the LCD. So here we are using the same header file as we were using the previous ones. The only thing we are using just when we push the button, first we execute the command, press the button, that text is showing on the LCD. Then when we put the first button, what we will see on the screen, and when we put the second button, what we see. So just we are just showing how the command of interruption, like one like a command, we are using a code that is working on a loop, and we have to put something in between them, like we are abruptly change the command or use something, it's kind of interruption. So that's why we are using, call it the global interruption or interruption. First we have to enable the interruption by using the EICRA and EIMSK. Then by the mask commands and encryption commands, we are enable the we have to enable the interrupts, and then we can use them. So first, if we enable them, then they are easily in use. So let's see what will be the output once we use that. So like that, here we are on the LCD, the press button command is already working, but once we press the button, you see that the commands change. And if we see then we press the second button, then you can see the second button command is showing now. So this is all in the lab 7. Then we go to the lab 8. Here we are using the in the lab 8 we are using a sensor, so we can see the output, like we are we are using a temperature sensor, and we want to check the temperature on the Arduino or on the screen. So the temperature measured on the measure in the in the temperature sensor, it will display on the screen. So if you are initializing the screen, then also we are using the same header file. The only thing we are using, that we have to enable the we have to initialize the input for the LM37, the temperature sensor, and show it as an output on the screen. So here we are using the code, how to first making an input, then for the ADCs and AVCs for the external capacitor references, and then enabling them by the interrupt activations, because here we are also using the interrupt command, like I'm changing changing the current or any other thing, so it will also execute on the LCD screen. So first we can see it, like no, that was no, that no, that is not the exact process I choose for that. Here we can see that it will show the temperature. Here we are using the LM35 temperature sensor on the temperature sensor. You can see that the temperature is 124 degree. Like if I'm increasing it, I am increasing it up to 90, then you can see that the increased temperature also change. So that is all, that is our lab 8. Now we are moving towards the lab 9. What we are doing in the lab 9, we are just giving a sine form. Like we are using by sine waves, we are blinking an LED and showing the same same waveform on our and showing the same waveform on our uh, oscilloscope, cathode ray oscilloscope. Nope, I don't want to open that. We have just to see the code. Like in the code, you can see that first we are initializing them PWM mode for the accuracy, and like we are using the PWM for the accuracy and more precision in the PWM. We can see that we can control the speed of motors, DC motors, and many other things. If we don't use that command, our line follower is abruptly stopped or and cannot make the sharp turns or not work smoothly. Same here, we are using that why we are using it. So when we are on lab 9, when we put it on, you can see that okay, it's not working. Why it is not working? Let's see. Open X file lab 9. You can see that here it's blinking, and if we want to see the view, we want to see the log digital oscilloscope. Here we can see that the sine form. So now we are done with all labs. This was the last task. We are done on the microcontrollers. Other labs are on the FPGAs, and in FPGA we are not dealing with the microcontrollers. We have FPGA controllers, and we are using them with the Quartus 13 and 15. So the FPGA, we have slight intro.
इस पे हमारा नोट गेट ऑन हो रहा है। अब जो है हमारा ए जो है हाई हो गया और बी जो है वो लो हो गया, तो इस पे हमारा नोट हाई है और जो है और ये जो है और एक्सोर ऑन है और एक्सोर ऑन है। इसमें जो है हमारा और बी हाई है, ए लो है, और इसमें और नोट और एक्सोर तीनों ऑन है हमारे। और दोनों जब ए और बी जब दोनों हाई होंगे तो हमारा जो है एंड और गेट जो है हमारा वो हो जाएगा।